Hello, and welcome to Watch This Space. I'm Jim Bridenstine, the NASA Administrator, and today we're going to talk about the James Webb Space Telescope, which is going to change the way we see not only our galaxy, but other galaxies and the entire universe. In fact, we're going to look back to the very dawn of time with the James Webb Space Telescope. Today I have two amazing guests. Dr. John Mather is NASA's Nobel Prize-winning scientist, and he's also the senior project scientist on the James Webb Space Telescope, and Dr. Thomas Zurbuchen, associate administrator of the Science Mission Directorate here at NASA. Gentlemen, thank you so much for joining me today.
Glad to be here.
Glad to be here.
Awesome. So Dr. Mather, tell me from your perspective, you're going to be the senior project scientist on the James Webb Space Telescope. How excited are you about this mission and why?
It is the most exciting thing I could possibly imagine to be working on. It is the successor for the Hubble Space Telescope, and it will be far more powerful and much larger and be able to see things the Hubble could never see.
Is that right?
So it can see things the Hubble could not see because it's larger and because it picks up infrared light, which the Hubble cannot do. So infrared light comes from things that are too cool to emit visible light. So you're emitting infrared light, and so we're building a telescope that could see a bumblebee at the distance of the moon just from the heat that the bumblebee gives off.
So this enables us in the infrared electromagnetic spectrum. This enables us to see potentially stars from a very, very long time ago. Obviously stars that wouldn't even exist today. But their wavelength, as it has traveled towards the Earth, the wavelength has expanded. And so it's in a different part of the electromagnetic spectrum, and that's what we're going to be able to see.
That's a big part of it. We see the most distant galaxies we can possibly imagine finding. We're looking for the very first ones that formed after the expansion of the universe began. We call it the Big Bang, and then what happened after that? The galaxies were formed, but we don't know how.
Dr. Thomas Zurbuchen, you're the Associate Administrator of the Science Mission Directorate, so you have responsibility over this program as well as so many others. Share with us, going back in time, how James Webb came into being ultimately as a program, and where you see it going in the future.
The questions that John just addressed are questions that have been with us for many, many decades. And the telescope, of course, came into being after, I would say, the success of Hubble, which really I would say is, without Hubble, there's no Webb, right? It's a magnificent telescope that still is the most productive science machine that we have up there. Close to 1,000 publications a year come from that one telescope. It's just out of any other realm. I mean, it's just so amazing. So basically what happened, something like 2 decades ago, scientists came together as part of the national academies and basically said, like, what would be the next big telescope? And they imagined Webb, which, as John said, is important for 2 reasons. The first one is it's cold. The second one is it's big. and those 2 characteristics really drove Webb and of course started a process that let it evolve to where we are today with a telescope in which basically all parts are built, right, and we're in integration and test.
So tell me, how complex of a spacecraft is this, and how complex of a scientific instrument is on board?
I'm going to talk about the spacecraft. I'll let you talk about the instrument. And the spacecraft is complex for 2 reasons. The first one is that it's a deployed mirror, right? So because the whole thing unfurls like some origami type structure, and then is put in place very, very accurately.
So tell me this origami type structure, you're talking about the spacecraft itself. Why does it need to be, what is the origami type structure for?
So imagine that the mirror itself, it's 6.5 meters, that the thermal protection shield, which again is there to cool everything down, is the area of a tennis court. So there is no rocket where that fits in.
So the thermal protection shield, just for the audience, we're talking about something that blocks the sun, so that ultimately we can have the absolute coldest mirror possible to detect the heat signature from infrared.
Absolutely. It blocks the sun 5 times over. That's how many such tennis courts we're deploying, kind of small aluminum foils that are out there deployed and, you know, out in space doing exactly what you said.
Okay, awesome. So that's complex in itself.
Oh, God, it is.
How many moving parts in order to deploy that?
Well, I mean, there's between 300 and 350 single points that move or kind of deploy in one fashion or another for this to occur.
Okay, and every single one of them has to work perfectly in order for this to deploy appropriately.
The vast majority of them, some of these, something like 50 or so, if they don't work, you know, we can work around this. The others, yes, they have to work. So in other words, you can't just have a half-deployed tennis court out there.
Okay.
It's really hard. It's really hard to actually fly the spacecraft, and it would not become as cold as it needs to be.
Okay. As far as the scientific instruments on board, how complex are those, and the challenges that we have?
Well, they're very complex. What makes them especially difficult is they have to be cold also. Some of them run at 7 degrees Kelvin, very close to absolute zero, and some of them at 40 degrees Kelvin, also very cold. So this is something that we can do, but it's not familiar.
So Dr. Zurbuchen, tell us where are we right now with James Webb, and what can we expect as far as when are we going to see the first science from it, and ultimately when can the public be inspired by it?
So the good news is all the parts of the telescope are basically built. They're standing in California in one company all together.
Good.
And are being integrated and tested. And we're right now kind of in the test program of the spacecraft. You know, that tennis courts on, you know, all this, the sun shield, all these things we're testing right now and are basically doing everything we need to do. Cooling, we're shaking it, we're blasting sound at it to make sure it can survive launch and so forth. Right afterwards, the telescope, Otis, the instruments and the telescope are being integrated with the spacecraft, and then the whole test program, or a subset thereof, starts again, and we make sure that this entire spacecraft with its instruments can actually survive launch and can be deployed, and then we ship it and get it to space, and if everything goes well, kind of in 21, it's out there and it starts deploying over a time period.
About about 2 weeks.
Yeah, John and I will be very nervous that time period, because we're going to get data back on the ground about all these single points, all these little puffs that make sure that this, this sun shield deploys, that everything goes just like planned.
As much as we've invested into this critically important scientific instrument, we have to get it complete. And you know, my understanding is we're on the 5-yard line. And as you mentioned, all of the components are built. All we got to do now is punch it into the end zone. We're all very excited about that. How confident are you that the new schedule that we're going to lay out, which says that we're going to launch in March of 2021, how confident are you that we're going to be able to accomplish that?
I am confident that this schedule is precisely sufficient, and also the funding that we have allocated is sufficient to get us over the finish line, like you said. Okay. We have to execute. We have the team. We have independent voices that have told us this is what it takes, this is sufficient. We have done exactly that, and now it's a matter of, you know, lining up the team, like you said, and carrying that ball.
We probably were excessively optimistic on how the integration and testing was going to go. The sun shield proved to be very complex, and deploying it and then refolding it, of course, has proven to be a challenge, and all of this has to be tested. We want to discover any challenges on Earth rather than after it's 1,000,000 miles away from Earth where it can no longer be serviced. So this is all part of the normal process. We discovered that the sun shield was going to be more complex than usual and that it was going to require more time. We called for an independent review board. They've now finished their assessments, and they've given them to us. Tell me, Dr. Zurbuchen, what are some of the biggest challenges, and what are we doing to address those challenges?
The key recommendations that came back to us, as you mentioned, we've accepted all of them, but the key recommendations that came back really focused on mission success overall. And one of them relates to really looking at this deployment sequence over weeks and months as we cool down, but the 2-week deployment sequence, in the same way as we look at a Mars landing, an entry, descent of landing. Again, a very nerve-wracking time in which it just has to work. There's no go-backs. It has to work.
Right.
And so basically we're putting in place a manager, very senior management, to just oversee that in isolation of everything else, or of course together with everything else, but that as a focus.
So a single world-class systems engineer that can oversee end-to-end the deployment of the James Webb once it's in space.
Exactly right. And so that was a recommendation that we have put in place.
Okay.
The second piece, and I would argue is probably the most important one, is that we focus on human errors and embedded problems. Embedded problems are human errors that we haven't found yet, but they're, if you want, asleep in the system somewhere, and they're going to come up either in integration and test, and if we're not careful, even worse, in space.
What NASA is doing is something that has never been done before. This is a very complex system. So I want to reemphasize, that's a great point that you just made. We want to find these things out on Earth, not in space.
Exactly right. And so what's really unusual with James Webb, so we've done integration and tests. We have 107 science missions right now, you know, some of them in flight, some of them on the ground. In all of them, we're doing integration and test or have done it, right? What's unusual here is the enormous complexity of the mission. So basically what happens is if you make a mistake, what happens? It costs a lot of money and a lot of time, just because this very complex machinery comes to a grinding halt right there.
So, so one small mistake has massive impacts.
Exactly right. So what you have to do, let's go back to your football analogy, you have to build a dream team.
Yeah.
Nobody can lose their role, and everybody has to communicate with each other. And so that actually, so it's here at headquarters, through NASA Goddard, you know, our managing organization, Northrop Grumman, where this is done, all the way to the shop floor with the technicians with the screwdriver in the hand. And it turns out that technician is actually more important than I am.
Yeah.
At this moment in time, probably in general, but in this moment in time, what she does on the floor affects this telescope in a direct fashion. And she needs to tell us if there's any worry, and needs to, in fact, with her colleagues, fix those worries right away. And so basically, it's really building that awareness. That's how we cut down human errors. We all make mistakes, but the impact of mistakes can be eliminated if we have checks and balances. We help each other. When I touch the screw, you check that I do it the right way and say, stop, that does not make sense. So that's the type of recommendations that we're going to build those systems and make sure that the vigilance goes up a lot.
As the senior project scientist, what are some of the things you're thinking about as you go through, they call it the commissioning process, where we're deploying you know, the sun shield, we're deploying the antennas that are going to communicate back to Earth. There's a whole host of different booms and pulley systems that ultimately are going to have to be deployed on this vehicle. What are some of the things you're thinking about, and how do you provide mission assurance once it's in orbit or once it's in space?
It's very tricky to deploy this thing, but we rehearse everything in advance.
Okay.
Many times here on the ground, we deploy and fold again. Then in space, we know what we're going to do. Much of the detail has already been worked out, day by day, hour by hour, minute by minute, what we're going to do when we get there. And we already have plans for what happens just in case something isn't quite right.
Yeah.
We have telemetry, which is instrumentation on board that tells us whether things have been done correctly. And we have a plan for what happens just in case. So for instance, we have on everything that's supposed to move, we have 2 ways to make it move. A motor has 2 sets of windings and 2 sets of electronics to control it. So one doesn't work, we try the other one. That's one of the ways that we know it should work. But we will certainly be watching it very carefully and thinking about it as it goes.
Awesome.
So this makes it, in a way, less hazardous than the Mars lander, which had to do it all by itself.
Absolutely.
We get to watch the step-by-step process and then to intervene if something's not quite right. And we have our backup plan.
There are concerns here that are very real and need to be respected, and we're going to follow the guidance of the Independent Review Board. But at the same time, we are going to be successful. We're going to get this spacecraft launched, and we're going to see back to the very beginning of time, which is going to be revolutionary in the history of science. So thank you, gentlemen, for joining me today. This is Watch this space. I'm Jim Bridenstine, the NASA administrator, and we'll see you next time.